All right, can everybody see the presentation?
Yes.
All right.
Right. Good morning, everybody. My name is Luis, and together with Jeremiah, we're going to walk you through the soft actor-critic, an off-policy maximum entropy deep reinforcement learning with a stochastic actor. Next slide, please. And I will walk you through a very key concept in reinforcement learning. We have already seen this in the lectures and as well as they explained in the previous presentation. The environment is a function that predicts the state and transition rewards. You can also understand this as the set of differential equations that you use to propagate to obtain the states. The states and observations are descriptions of the current world or environment. They can also be seen as representations because sometimes you don't have direct access to the states, but for just only of the observations. For example, images. You only have access to images, and from those images, you are supposed to extract some important features. You have the rewards that are the feedback from the environment, and they tell you somewhat if it is good or not, how good or bad it was to perform an action. The return is the cumulative reward, is the sum of all the rewards that you have collected along your way. The policy is the rule used by an agent to decide what actions to take. You can also see this as a controller that tells you the control actions that you have to take or you have to give to the system as inputs for to achieve a desired behavior. And the Q values and value functions, they are both expected returns, but they have a slight difference. The Q values are defined as the expected return if starting in state S, then taking an arbitrary state action A, and then forever act according to a particular policy. But the value function is also an expected return if starting on the state S, but always acting according to a particular policy. In this next slide, please. In the presentation, we'll talk about off-policy algorithms and on-policy algorithms. In off-policy algorithms, they update the policy that using previously recorded data, meaning from old experiences that have been stored in a part of the memory. And this is done regardless of the policy used to explore the environment. On the other hand, on policy algorithms, they evaluate or improve the policy that is used to explore the environment. So they evaluate and improve the same policy. They only have one policy. And the thing with reinforcement learning is that there's no direct supervision. So it is basically a trial and error process where the agent is just moving around and making mistakes, making good actions, and with that, trying to learn. And the final goal is to reach an optimal behavior by using the Bellman equations that give you the necessary optimal conditions, the necessary conditions for optimality. Next slide, please. So there are many reinforcement learning algorithms so far, and we will build our way up to the soft actor-critic by talking about specifically 3 algorithms. We will talk about the deep Q learning, the PPO, which is called Proximal Policy Optimization, and the DPG, which is a deep deterministic policy gradient, and the A2C, which we will see later. For the DQ learning, I'll talk about. Can you go to the next slide?
Yep.
For the deep Q learning, I'll briefly talk about what is the Q learning. In Q learning, we have a table that tells us what are the rewards that we expect to obtain at a given state by taking certain actions. And at the end, we can just choose those actions that lead to the higher rewards. And that's how we can see that Q table as a cheat table. The problem with this table is that as the state and action dimension grows, the table will grow as well, up to the point where it is unfeasible to have a table because of memory constraints or the time constraints, the time that would take to access the values of this table. When this happens, and this table represents the Q values or the value function that I talked before. Can you go next? So when instead of having a table, we can use a nonlinear function approximator, a neural network, for example. And that's what the deep Q learning does. So instead of having the table that is our cheat table, now we have this function, which is a neural network, to give us the values, which are the expected returns given a state and an action. And in deep Q learning, the action space is discrete, and this is an off-policy algorithms. It learns about the greedy strategy while following a behavior that ensures an adequate exploration of the state space. Next slide.
Okay, so we're going to start and talk about proximal policy optimization. Just to kind of explain the overall structure of the paper, the authors evaluate their soft actor-critic algorithm compared to these other algorithms that we're going to explain here. So kind of giving an overall summary on how these other algorithms compare to the soft actor-critic to better understand the performance later on. So with proximal policy optimization, it's an on-policy algorithm. So that means it explores the environment by sampling actions according to the latest version of the policy. And it iteratively optimizes its policy by adjusting the probabilities of the actions to lead to higher returns until the optimal policy is reached. So in basic policy gradient optimization, you want to have your new and old policies relatively close to each other in parameter space, because making too big of steps can cause the model to kind of collapse and lead to bad performance. So you want to keep your iterations and steps from the old policy change to new policies change relatively small. But this can lead to inefficiencies. So proximal policy optimization tries to mitigate those inefficiencies by determining what the largest possible safe step in terms of going from an old policy to a new policy is, and taking that step to stay within a range that prevents the model from leading to bad performance by collapsing, essentially. So this is kind of mainly done by looking at our objective and new policy terms. So essentially what happens is the objective is determined by taking a ratio of the new policy distribution to the old policy distribution, determining your advantage, which is essentially how much better a given state action pair is compared to an on-policy action, versus a clipped version of the distribution ratio, which is bounded by 1 minus eta and 1 plus eta, also multiplied by advantage. It takes the minimum of either of those two terms, uses that to update to the new policy. Here we have a graph that kind of shows our objective function. You can see that it's bounded at 1 plus eta and 1 minus eta. The advantage is positive, then you're bounded between 0 and, or you're bounded at 1 minus eta. So that's the largest possible improvement that you can do in your next iteration towards the policy without taking too large of a step, essentially. And conversely, when the advantage is negative, we're also bounded to ensure that the penalty is within a safe bound when we're moving towards our new policy. From here, we're also going to explain kind of A3, which is asynchronous advantage actor-critic. So this is an actor-critic structure and algorithm. So it uses both on-policy gradient iteration and off-policy Q-learning. So it kind of is an approach of taking on-policy and off-policy methods to create a model. This kind of gives us the advantage of using the advantages of on-policy gradient optimization, which is kind of what we explained before, allowing us to improve our policy directly based on actions within a policy. But off-policy Q-learning is more sample efficient because you can use policies, or you can use past experiences that aren't necessarily based on the current policy to still improve your learning. So it kind of uses both of those portions to, and marries them together to give you both the best of both worlds, essentially. So Q-learning, quick basically is using an approximator Q function that's based on the Bellman equation to evaluate your value. So like I said before, the optimization is on policy in the actor-critic algorithm, and Q-learning is essentially used by the critic to provide feedback on the current policy. So if we go here, we can kind of see an additional structure of specifically the asynchronous advantage actor-critic. So the main difference in terms of conventional actor-critic algorithms versus A3C is that you have multiple actors working in parallel that report back to the same critic. So you can have different interactions and experiences within the same environment working concurrently. So that's kind of the asynchronous component. And the critic then uses your Q value and the pi term to evaluate how well the current policy is acting within the environment, reports back to the actors, and kind of does that iterative process over and over again. So that's why it's called asynchronous advantage actor-critic. And
on the DDPG algorithm, which is called the deep deterministic policy gradient, this is an actor-critic architecture where the value function is approximated by the critic, which is a neural network, and the output of the critic is the value function, which is the expected rewards. And the actor function is also a neural network that is approximating our policy. And the actor is optimized using the value given by the critic. That's why the critic is called the critic, because it kind of like criticizes, how the actions were taken by the actor are, if they are good or bad. And the critic is optimized using the reward that comes from the environment. This deep deterministic policy gradient used for continuous action spaces. Before we saw that the deep Q learning was used for discrete action spaces. The reward is used to optimize critic, and the output of the actor or our policy is deterministic instead of a stochastic. If it was stochastic, it would have a distribution. Go next slide, please. And the way that the algorithm uses to explore the state space is by adding random noise or random process noise. So the output of the policy, to the output of the policy, this random noise is added. And so that in that way you can explore the environment and update the policy. It uses target networks for the actor and the critic. The target networks are very important because they have been proven to stabilize the training. The target networks are copies, literal copies of the actor network and the critic network. And these target networks are slowly updated over time. And these slow updates or soft updates tend to be stable. It uses a replay buffer. So it collects previous experiences in the form of the tuple of the previous, of the present state, the action taken in this state, the reward obtained, and the state that we landed at after taking action A. At each time step, the actor and the critic are updated by sampling a mini batch uniformly from the buffer. In this way, the mini batch attempts to reduce the correlation between samples. And it uses batch normalization since the measurements or the variables that we're dealing with may have different units or different magnitudes. Next slide. The actor is updated using the policy gradient that you can see here. And the critic is learned using the Bellman equation that I showed you before, like in Q learning. And here's an example of a real implementation of an actor-critic algorithm. Something interesting to note is that I haven't seen people when people use the actor and critic networks, they don't talk about neurons. They call them just units or nodes. So if you stumble upon that difference, just notice that they technically are made of neurons, as we can call them in the computer science field, but they are also called nodes or units.
So the soft actor critic is essentially, shares a lot of similarities with two other algorithms, the DDPG, just explained by Luis. And essentially the difference between the soft actor critic and the DDPG is that one, the soft actor critic includes entropy in its equations, which we'll go into more detail in the next slide, but it also uses two Q functions, whereas DDPG uses only one. So the purpose of the entropy is to encourage learning later on. So you want to reward the model by taking actions that approach the optimal policy, but doing it as randomly as possible in terms of its actions. So where DDPG adds noise, soft actor critic has an entropy term, and the reward has an entropy term included within it that's proportional based to how the value of the entropy of the given action. So this is basically a form of entropy regularized reinforcement learning. You can think of entropy as the measure of randomness that a random variable has. So the higher the entropy, the more random the variable. So like I said before, the policy should act to maximize expected future return plus future entropy. We can look at the optimal policy equation here. You can see there's the alpha H term, and that's essentially the additional entropy term that's included within it. So this basically acts to give the agent a bonus reward at each time step that's proportional to the entropy of the current time step. So over the course of time, this essentially rewards policies by acting as randomly as possible. And the reason, again, that we want to do this is because by acting as randomly as possible, we still encourage exploration later on versus exploitation, which is specifically rewarding or specifically adopting high reward policies and not doing as much exploration later on, which is a limitation of other algorithms such as PPO. Like I said before, soft actor critic has two Q functions, and it takes the smaller of two Q values to form the targets for the Bellman loss error functions. And essentially, this tells us how closely the approximator Q functions are coming to satisfying the Bellman equation. And again, there's an entropy bonus at each time step within the Q functions and the value equation. And this is kind of the overall structure that the authors within the paper used for their soft actor critic algorithm. You have your initial policies, you set your target parameters, take your actions, execute it within the environment, observe the next state to essentially create a replay buffer, which is it contains a set of previous experiences. This can include experiences from not the current policy, but you don't want it too large to encompass all of the policies that have been done in the past. But you do want it large enough to not contain only just current policies, but enough to prevent overfitting within your model by using all previous actions. From there, we iteratively compute the targets for the key value functions, update them using gradient ascent, update the policy based on how well the policy is performing based on feedback from the critic, using gradient ascent, and update the target networks. So that's kind of the overall algorithm structure. In this paper, the hyperparameters that they used Atom as an optimizer, Their learning rate was 3 times 10 to the negative 4. Replay buffer size of 10 to the 6. They had 2 hidden layers, 256 hidden units per layer. Each mini batch had 256 samples. Their non-linearity function was also ReLU. And their discount value was 0.99.
So this algorithm was tested in 6 different environments from OpenAI, and they are based on the simulator Mujiko. The most complex of these environments are the ant environment and the humanoid, where in the ant environment you have 111 states and 8 actions. And the most complex of all of them is the humanoid, where you have 376 states and 17 actions. You know, the states may include, for example, the angle of the joints between, I don't know, the legs, or the angle of the hips, or the linear velocity of the limbs. There's a detailed, not such a detailed, but kind of like a detailed explanation in the OpenAI Gym website. And there's also another implementation of the humanoid environment by RL Lab that contains 142 states and 21 actions. Can you go next slide? And here are the results. In orange, we can see are the results of the soft actor-critic algorithm. We can see that it outperforms the other algorithms, the DDPG, which has been widely used, the PPO, the SQL is a subset Q-learning, and the TD3, which is a twin delay, the actor-critic. And it outperforms in the most complex of the algorithms, which is the humanoid and the ant environment. And we can see that in the Walker environment, where you have 2 limbs and it has to walk only one direction, it is not better, but it is, I'd say, comparable to the other algorithms. This shows that within the same amount of time, the algorithm is able to, because it has a stochastic actor, it is more sample efficient. So it is exploring the environment in a better way. Another thing to notice is that if you want to implement these algorithms, have to take into account that the results that we're showing here are measured in millions of, not measured, the time domain is in millions of steps. So this will take a long time to simulate if you're doing it in, let's say, in your laptop, because I have tried, so make sure that you have that into account. Can you go to the next one?
Yes.
The stability of the algorithm is also tested against different parameters. The first one is how good or bad this algorithm will be if, instead of having a stochastic policy, you have a deterministic policy. So on the left-hand side of the slide, they implemented a deterministic version of this algorithm. And what we see here is the average return. In red, it is when the policy is deterministic. And we can see that there's a huge variation of the average return when the policy is deterministic, whereas when it is stochastic, the variation is not too much, like in the deterministic case. They also tested how the scale of the rewards impact the average return of the system. So when the rewards are not scaled, for example, or come as they are, you achieve like a medium and not such a good result, which are the blue line in the center of the slide. But if you over scale the rewards, you also do not achieve such a good reward. So, and the best scaling factor for the reward in this case is 10 in the green line. That tells that too high rewards do not have such an important meaning in the environment, but too little rewards also do not have a meaning. So there's like it has to be a trade-off. And on the right-hand side, we have the target smoothing factor, which is the amount of updates that we do to the target networks. So, and this value goes from 0 to 1, with 1 meaning a hard update, which means we take all the value and update it to the target networks, and 0 means 0 update. And in here, the the worst value, it is the highest, which is 0.1. And with a 0.1 update, well, the smoothing factor, the average return is very, very bad. And that's our presentation. If you want to go into more reinforcement learning resources, there are a lot of packages that have implemented the reinforcement learning algorithms in Python, either in TensorFlow or PyTorch. But also MATLAB has their own reinforcement learning toolbox. Since 2019, it's fairly new. And the current release has more algorithms implemented in their system. Thank you. Do you have any question or something that we want to clarify?